So since it's been 2 weeks, let me just recall for you the basics. We did last 2 weeks ago. So we have cochain complex.
Yeah.
And we have a decreasing filtration. And we lose FP, which implicitly I'm going to assume is finite, at least in each degree, so that our spectral sequences converge. Anyway, we then define the pages of the spectral sequence, ER, PQ. It's the X in FP of CP plus Q. So recall P is the filtration index and P plus Q is the cochain degree. Such that D of X is the filtration level P plus R over D is filtration level P minus R plus 1 intersect FP and CP plus Q. So those are the differentials you divide out by. And then we also divide out by the Y in filtration level 1 more with the property that dy is greater than P plus R. Okay. We have a map induced by D, which is called dr, goes from ERPQ to ERP plus R Q minus R plus 1. So it has total degree 1, and it raises filtration degree by R, which is what you see here. And the cohomology of this complex and differential is the next term in the spectral sequence. Okay? And I guess the last thing to say is that under the finiteness assumptions, the spectral sequence in each degree stabilizes at some finite stage, and EPQ is, if you take the associated graded the cohomology with its induced filtration, and you look at the gradient degree P of HP plus Q, this is E infinity. So if we think of the spectral sequence as being a sequence of pages, and I'll think of the first quadrant spectral sequence, so the page has only terms here, so we have E R0, 0, E R1, 0, RP 0, E R0, 1, Q, E, R, E, Q, if you look at, well, let's just say a word about the differentials first. Color chart. So the differentials increase filtration degree, so they go to the right and have total degree 1. So if you look, total degree is simply given by these diagonals. So if you look at dr, it will go over R and down R minus 1. So it increases total degree by 1. So it goes from one of these lines, I can draw it very well here, so from one of these lines to the next one up. Okay. And And then by the time you get to E infinity, if you look along one of these lines, you see the associated gradients of filtration in that cohomology. So if you, at E infinity, if we look along the line here, P plus Q equals N, we get, what do we have? We have E infinity 0 N down to E infinity N 0, and these are the associated gradients of this filtration F star cohomology. So this one would be F naught of H N divided by F1 of H N, this one. And this one would actually be F N of H. Is that right? Okay. So this is a sub-object, actually, the subgroup of cohomology, and this one is the last quotient. And the intermediate ones are subquotients. So that's what that thing looks like. That's what a spectral sequence looks like. And there were two general facts that I wanted to present last time that I didn't run out of time before I could do them. And these are degeneration statements. And the two statements are about degeneration at E naught, which is really the trivial case, and degeneration at E1. A spectral sequence degenerates E naught if and only if D in the chain complex is 0. So maybe I should say, maybe I should remind you what it means for a spectral sequence to degenerate. So, do that here, definition. A spectral sequence degenerates at ER if ER equals E infinity for all P. So if there are no differentials after ER, the whole spectral sequence. So it has two parts. Part 0 is a spectral sequence degenerates at E naught if and only if the differential in the chain complex is trivial. It's a completely trivial case. Cohomology is the chain complex. Not really very interesting. Much more interesting is that the spectral sequence degenerates at E1 if and only if the differential from the chain complex to itself is strictly compatible, well, strictly preserves the filtration. And I guess I should define that, i.e., D, image of D intersect FP is equal to D of FP. That's what it means to say a map strictly preserves a filtration. If you have a map between two filtered objects which preserves the filtration, it strictly preserves the filtration if it satisfies the analog of this. Namely, if something is in the image at filtration level P, then you know it comes from something, but you don't know where it comes from. You have a one-sided bound on where it comes from because the map preserves the filtration. But in fact, staying strictly preserving is you can find something in that same filtration level that's equivalent to the spectral sequence degeneration. And in linear algebra, this is an incredibly important condition. It comes up a lot, especially in projective geometry. Okay. Well, maybe I'll do the trivial directions of both of them and leave the slightly non-trivial directions to you that are in the notes. Well, suppose, so the trivial direction is the first of the zeroth one is suppose D equals 0. Then remember all dr are derived from D. Well, if D is 0, all these derived dr is 0. So that implies that dr equals 0 for all r, and hence the spectral sequence collapses. dr equals 1 for all r. Particular infinity equals 1. Maybe I'll do the opposite direction of this one because it is so easy. So, on the other hand, suppose conversely, suppose the spectral sequence collapses at E naught. So E naught is equal to E infinity, or it's equal to ER for all R. Okay? I'm going to prove by induction that B maps FP into FP plus R. And now this will imply the result. If this is true for fixing P for all R, eventually by the finiteness assumptions in the spectral sequence, these terms are 0 for sufficiently large R, and therefore D restricted FP is 0. You do that for every P, and again, using finiteness as a filtration, you see D vanishes on all of all the cochains. Okay, so this is what we need to do. Well, so suppose by induction, suppose from there, the D of FP is in FP plus R minus 1. And the spectral sequence degenerates up to this level, but no further necessarily. But we look at dr, mapping dr dq into dr d plus r d minus 1 plus 1. Well, first of all, because the spectral sequence has degenerated through ER, this is E naught dq, which is simply the x in FP, so it's the dx is in FP plus R, divided by y in FP plus 1, so it's the dy is in FP plus 1, plus d of f. Well, sorry. That's it. The other term vanishes because it's contained in this one. In this case. Wow, sorry. I said it this way. This is FP of CP plus Q over FP plus 1 of CP plus Q. That's what E naught PQ is. But it's also ERPQ, which means that this is the collection of X in FP, so it's a DX is in FP plus R, all those two stuff that I guess I should write it down. I'm not going to do this, folks. I'm going to leave that. It's in the notes. Okay. So let me pass to the other case, the first case of the lemma. So suppose, again, I'll do the easy direction. D is strictly compatible with the filter. I'm going to show that E1 PQ equals DR PQ for all R. Okay? Well, let's just write down ERPQ and use the strictness to simplify it. So ERPQ is X in FP of CP plus Q, such that DX is in FP plus R over Y in FP plus 1 plus Q is the DY in FP plus R plus E of FP minus R plus 1 intersect FP. So the first thing to observe is using strictness of D, you have something in filtration level P minus R plus 1. You take its image and it's in FP, then this is already contained in D of FP. This is equal to D of FP. This is because R is, I guess, greater than or equal to 1 here. On the other hand, let's look at dx. So dx is in FP plus R. That implies there exists a y in F. Well, yeah, that implies there exists a y in FP plus R such that dy equals dx. Again, using strictness. Okay? But now I'm free to, and R is greater than or equal to 1, so this y is an element here. Okay? It's in FP plus R, so it's certainly in FP plus 1, and d of it is in FP plus R, because it's equal to dx. So I can vary x by such a y. So in fact, that shows you that everything in the numerator here has a representative mod the denominator where dx is 0. So that shows that this is really the x in P of CP plus Q, such that dx equals 0 modulo d of FP plus the y in FP plus 1. Such that d of y is 0. While that is infinite. That's the definition of infinite.
Sorry, how did you find that y?
I looked at dx. So it's an element in FP plus R, and it's clearly in the image of D. So I use strictness to say that there's a y in this filtration level with the same D. And now I'm free to vary x by the y because I'm working in this quotient. And that allows me to assume my numerator is made up of things where D is 0, and then I have to divide out by this. So I guess I've shown for any r greater than or equal to 1, that's the only thing I needed here, r greater than or equal to 1, dr is equal to E infinity. The reverse one is slightly tricky, at least the way I sorted it out. You do a downward induction on P and an upward induction on R, basically. Anyway, it's in the notes.
In the case of the double complex, does one just say that the horizontal differential is 0?
Yes. No, it does not. So let me show you. Let me show you an example, which I'm just going to state the result that I'm going to use out of differential geometry without proof. But if you have a compact Kaling manifold, so X, compact Kaling manifold. So this means it's a complex manifold, it's a compact complex manifold, and it has some differential geometric condition. All projective, smooth projective varieties satisfy this condition. Then there's a result that's called the DD bar limit. So the double complex here is the differential forms of type DQ and X. And the two differentials are D and D bar. Okay, so we have this double complex. Round D is not 0, but yet the double complex spectral sequence collapses. So the spectral sequence from, let's call it HQ of omega P, converging to the usual cohomology that the complex coefficients, collapses at E1. In other words, these are the associated gradients of the filtration and the cohomology. And the reason is something called the DD bar limit. So if you have an alpha in, let's say, omega DQ, D alpha equals 0. So this, of course, means D bar alpha equals 0 and D alpha equals 0, because we've got a homogeneous, bihomogeneous term, and D of it's got one component over here and one component over there. If the cohomology class of alpha equals 0, ordinary D cohomology, then alpha is D bar of some beta. So you can take this class and write it as both D bar of something and D of something, but in fact you can push it down through the whole square and write it as D bar of something down here. And from that, you see the spectral sequence collapses. But yet these differential.
The induced map on the first page is correct.
That's right. The map induced by D on the D bar cohomology is trivial. That's just it. Okay. All right, so I've been talking, so now I want to shift gears and talk about homology spectral sequences. So I've been talking so far exclusively about cochain complexes and decreasing filtrations. Now I want to switch gears and talk about chain complexes and increasing filtrations. And just say a few words about what's happening there. Increasing filtrations. On chain complexes. So this is, formalism here is completely analogous. Some signs get reversed, and that's about it. So we have a chain complex with a boundary map, and we have an increasing filtration. That's A, including A+1, and so on. Again, same sort of finiteness assumptions. Then there's a spectral sequence, a homology spectral sequence. Its term ERPQ will look very similar to what we have over here. It's the X in filtration level P of CP plus Q, such that the boundary of X is in FP minus R over, again, Y in FP minus 1, so it's the boundary of Y is in FP minus R, plus D of FP plus R minus 1, and you set FP and CP. Should look formally very similar to what we have over here. Except that we can see. And there's a differential, dr, that's ERPQ into ERP minus R, Q plus R minus 1. So it lowers filtration degree by R, and it lowers total degree by 1, so it raises the Q here. So if you think of these differentials, now they go to the left and up, and they lower total degree by 1. Now, one way to derive the homology spectral sequence is to realize that there's no difference between homology and cohomology. It's just a question of do you index positively or negatively. So completely formally, there's no difference. If we have a chain complex, which I'm going to take to be free to be in here, a boundary map, and an increasing filtration, I define a cochain complex, Ci is C minus I. So I just take the same group, same free-of-getting group, and flip it over in the opposite degree. And now D from Ci to Ci plus 1, well, this is just the boundary map from C minus I to C minus I minus 1. So cochain complexes and chain complexes, they're all the same. Just a question, if you flip the index over, you'll turn a chain complex into a cochain complex and vice versa. Okay. Do exactly the same thing with the filtration. You define FP to be F minus P. And if this one is increasing, this one will be decreasing. Now, so then if you started with a chain complex with a filtration preserved by a boundary, you do this, you get a cochain complex with a decreasing filtration preserved by D, so you get a spectral sequence. If this thing was concentrated in positive degrees, as we usually think, this of course will be concentrated in negative degrees. It'll be a third quadrant spectral sequence. Everything will be negative, but if you just flip the signs on that, you get back a first quadrant sequence, and you will produce the homology sequence that I've written down over here. So completely formal. So we don't have to go through all the analysis of these terms again. And notice what happens is the index just gets flipped. You flip over with a minus sign, then you take these differentials which go up, and then you flip back. Well, the P got flipped to minus P, got flipped back to P, but the R only occurred after you'd flipped once, so it gets flipped. So that's why the sign in the R here is the opposite of the sign there. R plus 1 is the opposite. Just comes from this involution. That, however, is not the interesting relationship between homology spectral sequences and cohomology spectral sequences. That's just the way you see there has to be a homology spectral sequence, because it's really the same. The more interesting relationship between homology and cohomology spectral sequences is one based on duality. So suppose we start with a chain constant and duality of spectral sequences. So suppose we start with a chain complex and an increasing filtration. And here I'm going to take the chain groups to be free abelian, so I'm going to go to some kind of derived category. I define the cochain complex to be Hom of CK is Hom of the chains CK into Z, and the differential CK to CK plus 1 is the algebraic dual of the boundary map. Okay. So notice I didn't, in some categorical sense, this should be put in negative degree, but it's not. Notice there's no flipping of indices here. All right. And then I define the decreasing filtration on C star to simply be the annihilator of F T minus 1. The things that annihilate that level of filtration. And now you see directly that since this is an increasing filtration, the annihilators of bigger and bigger subsets, bigger and bigger subgroups, are smaller and smaller. So this is a decreasing filtration. This is an increasing. This is increasing. And this is decreasing. And suppose, as is typically the case, that in CK we had F minus 1 CK equals 0, and that goes up to FK of CK, which is all of CK. So suppose we had a filtration like that. Let's just think about what the dual filtration looks like. So F naught would be the annihilator of 0. Well, everything annihilates 0, so this would be all of CK. And Fk plus 1 of CK would be the annihilator of Fk of CK. That's the annihilator of CK, and that's 0. So the dual filtration would start at F naught, which would be all of the dual, and go down to Fk, and then Fk plus 1 would be 0. Well, if you have filtrations dual in this sense, then you get two spectral sequences, a homology spectral sequence and a cohomology spectral sequence. And those spectral sequences are dual. You have to be a little careful what you mean by dual. They're dual in exactly the same way homology and cohomology are dual. If you work over a field, they really are dual. But if you work over the integers, the torsion gets shifted around and duality is really in the derived sense. So I'm going to try to make that precise. We'll see an example of Serre spectral sequence in just a minute. So it'll be clear, at least at E2, what the duality means. All right. Okay, so the next thing I want to do is talk about the Serre spectral sequence of a vibration. This is predated by something called the Serre spectral sequence of a map, but Serre spectral sequence is so beautiful and so important that I thought I would do that one. It's also a little easier to work out than the Serre spectral sequence. But I think it was inspired by the ordinary spectral sequence. So the Serre spectral sequence. Vibration. So I'm set up the following. We have a map between spaces, E to B, topological spaces, and this is a Serre vibration. Now, in order not to get into the world of twisted coefficients, I'm going to assume something we've seen before. I'm going to assume that B is path connected. B is path connected. And the fundamental group of B, based at the favorite base point, acts trivially on the homology and cohomology of the fiber. I think that's a bad name for fiber since it looks like a filtration. So F naught is P. Okay. So this will allow me to avoid twisted systems of coefficients. Okay. Of course, we've seen before that this means that the homology and cohomology of any fiber, the inverse of any B, is identified with the homology of naught, and similarly. And then just remind you of what that identification is the base. Here's the base point. And here's your point B. You simply, the space is path connected, the base is path connected, so you simply take a path gamma from, let's say, B naught to B. And you look at, well, many ways to go. So let's look at P inverse of gamma. And we have two inclusions. We have F naught, the inverse of this point, and F B, the P inverse B. They both include the end. I claim both maps are homotopy equivalences, weak homotopy equivalences. And that follows immediately from the homotopy long exact sequence of the Serre vibration. Because so this is a Serre vibration over a point, this is a Serre vibration over an interval, and this is a Serre vibration over a point. Of course, the homotopy groups of the total space in these two cases are the homotopy groups of those particular fibers, since the total space is the fiber. The point is that you have a long exact sequence for the homotopy groups of this space to the homotopy groups of the interval to the homotopy groups of the fiber. So the conclusions are homotopy equivalent. You write down, maybe I should say it this way, write down the homotopy long exact sequence for this, and for this, for this, and the maps between them, the isomorphisms on the fiber, and therefore. So once it's a weak homotopy equivalence, that implies it's an isomorphism on homology and cohomology. So This is an isomorphism, this is an isomorphism, so you get an isomorphism between the two passing through a gamma. To do that, in general, you need to choose a path. But now I want to invoke my hypothesis that the fundamental group acts trivially. If I choose a different path, mu, between these points, then I have an isomorphism determined by gamma here, and an isomorphism determined by mu here. And if you go around this loop, the isomorphism determined by gamma followed by the inverse isomorphism determined by mu is the action of this loop on the fundamental group. But that's trivial, meaning that the path gamma and the path mu produce the same isomorphism. So that's how these fibers have their homology and cohomology identified. You have to choose a path between them and then look at the part of the fibration over that path. In particular, if you have a cycle here, zeta naught, and a cycle here, let's say the dimension, so these are cycles. If you can find a chain here, k plus 1, whose boundary is this one minus that one, then the homology class of zeta naught here and the homology class of zeta b here are identified under this equivalence. So that's another way to think about the equivalence. So if this is a chain Z, and boundary Z is zeta b minus zeta naught, and Z is in this gamma, naught is identified under this isomorphism with the homology classes. Okay. All right. So that's our setup. Now I want to define the spectral sequence. I'll work in homology here by filtering the chains. Okay, so the spectral sequence comes from filtering the chains. Chain complex. Now, since we're working with vibrations, it turns out to be much more natural and much easier to work with singular cubes instead of singular simplices. Okay. So our chain complex is made of singular cubes. Now, when you think about this for a second, you think, oh yeah, what's special about a simplex? You can use a cube. The basic properties that you need well, the boundary of a cube is a finite collection of cubes, and you can use the orientations to assign the signs. So there's a natural boundary map of a cube, sigma, summation plus minus 1 times various quote faces. Epsilon A is plus minus 1, and sigma A is a minus 1 phase. So for example, the square, you would get, what would you get? Plus this one, plus that one, minus that one, minus that one. Okay. And you identify each face with a subcube in the obvious way. You've dropped one of the indices out. It's either 0 or 1, and use all the other indices in the standard order. Okay. Pretty clearly, boundary squared is 0. And you have to check the axioms. long exact sequence of a pair, sort of obvious. The one that's usually thought of as the most delicate is excision, or equivalently Myrivotorus. And that relies on the fact that for simplices, that is, you take barycentric subdivision, you can make the simplices in your chain arbitrarily small, and thus small with respect to any open cover that happened to be given. For example, the UV cover of the Myrivotorus. Well, you can do the same thing with cubes. If you have a cube, you can simply, in fact, it divides even faster. It goes to zero even faster because simplices get long and skinny and they go down very slowly, but they go down. Okay, so you have Myrivotorus, you have a chain complex that has long exact sequences of pair. Amazingly, what fails is the dimension axiom. Because a cube always has an even number of faces. So if we think about the cubical homology naively defined of a point, well, there's a z in every dimension because there's exactly one cube of any dimension mapping to a point. So let's take the singular cubes mapping to a point. So singular k cubes of a point. Well, there's exactly one cube. I'm supposed to take the free abelian group generated on that cube. So this is z. Likewise, k minus 1 of the point is z. What's the boundary map? Well, you have to add up all the boundaries with these signs. So if I start with this cube mapping to a point, and I take the boundary, well, these things cancel out in pairs because they're all the same map. So in fact, for cubical homology, the boundary map is 0, and so the homology of a point is calculated this way, be a z in every degree. In fact, Massey wrote a paper about singular homology, and he forgot this point. However, there's a simple remedy for this. Instead of taking all cubes, all singular cubes, like qk of x be the set of non-degenerate, so I'll call non-degenerate cubes, singular cubes. So a cube mapping in, so a map of a cube of some degree into x is degenerate if the factors IP to IP minus 1, forgetting the last chord. So if this mass factors through the projection under the first p minus and all but the last coordinate, it's said to be degenerate, otherwise it's non-degenerate. And we take the set of non-degenerate k cubes. Okay. And we'll let the kth cubical chain complex, this cubical chain on x is just the free abelian group generated by these non-degenerate cubes of degree k. And then finding linear combinations within your coefficients of these non-degenerate cubes. But you have to check, first thing you have to check is that the boundary map preserves the non-degenerate cubes. Now, actually, strictly speaking, you have to do that if you work in a quotient space of, anyway, I'm going to work in this subspace. But the point here is there are two faces that you know nothing about as far as the degeneracy condition is concerned. If you take the face where you set the last coordinate equal to 0, or the face where you set the last coordinate equal to 1, those two faces, they may not be, they may or may not be degenerate. But they cancel out because, right, so let's look at the two-dimensional picture. So I'm supposing this is non-degenerate. So it's mapping into X. And now, what happens here? So where the first coordinate and second coordinate, where the second coordinate is 1, so this is the face T1, 1. This is the face T1, 0.
Are you worrying about that the image of this map will not map to degenerate
It's
stuff?
degenerate thing.
Yeah. So maybe the top just map to a point and the degenerate. So the map is not really fun.
Yeah. Well, listen.
You say suppose the boundary is degenerate, work back.
Sorry?
Suppose the boundary is degenerate,
Yeah.
you can work back.
Well, no, I'm worried about, so the boundary is a linear combination of singular cubes. I'm worried one of them might be degenerate. No. It's not that the whole boundary is degenerate. Well, let me think actually about the others where I don't drop out the last vertex. So suppose I look at a face T1, TK, 1, TK plus 2, up to TP. And then, okay, so that's one of my faces, and I'm really thinking of that as a map of a P minus 1 simplex in. But if, yeah, so suppose I have both. So I claim if the original simplex, I see what I have to do. Didn't do this right. So this is not the free abelian group generated by the non-degenerate simplices. This is the cubical, the free abelian group generated by all singular cubes divided by the free abelian group generated by all degenerate cubes. Now that is abstractly more than abstractly, that is canonically isomorphic to the free abelian group generated by the non-degenerate cubes. You have a set and you divide it into two pieces. The free abelian group on that set The full set is obviously the sum of the free deviating group on this piece and that piece. But I want to think of it this way.
So in the old setting, you just send those bad things to 0. That's what you.
Yeah, so what I need to know is that when you take the boundary, that I get an induced map on these quotients. So what I need to prove is if you have a degenerate simplex and you take its boundary, you get a degenerate simplex. You get a linear combination of degenerate simplices. That's what I need to prove. So sigma mapping IP into X is degenerate. Then boundary sigma, which is summation of the signs epsilon A, sigma A, is also a linear combination of degenerate simplices. That's what I need to prove. Now, if you take a face where you delete a coordinate direction that's not the last coordinate direction, you still have the degeneracy induced. The only ones that aren't obviously degenerate are when you delete the last coordinate, +1 or 0. So you get two simplices which may not be degenerate because you've dropped out the last coordinate, so you don't know anything about them. But because of the degeneracy, they're equal as maps. And therefore they have opposite signs, so they cancel out. So the faces T1 of 1 in the middle, TP, are degenerate. They inherit their degeneracy from the ambient degeneracy. But we're left with T1, TP minus 1, 1, and T1, TP minus 1, 0. These are not necessarily. But as maps, they're equal. And they go to the opposite side. The opposite faces in any cube, one's got a plus and the other's got a minus. So you get a well-defined map on the quotients. And now if we compute so everything I said before still works. Boundary squared is 0. The subdivision shows you Myers-Briggs or excision holes. That still works. But we have to compute the homology of a point now to make sure that's right. Well, how many non-degenerate simplices cubes are there in a point? Well, there's a 0 cube. That's not degenerate. But every other cube is degenerate. So in fact, your chain complex for a point is concentrated in degree 0. See, what happens for the simplex is the number of faces in a simplex alternates between even and odd. Is that right? Yeah. So the interval has 2 faces and the triangle has 3. So they alternate between even and odd. The odd ones give you a 1 because the signs cancel out as much as they can. So for the odd one, you get the boundary map as an isomorphism when you're talking about a point because you have an odd number of faces that cancel out to give 1 face. And when you have an even face, an even dimensional, an even dimensional simplex has an odd number of faces, so that map is +1, plus or minus 1. You have an odd simplex that has an even number of faces and the map is 0, so you get trivial homology, except at the point. It's a funny thing about the cube, always has an even number of faces. Okay, so that's what we're going to do. We're going to take the, what I'm going to call CC star of X. So the cubical change. And that implicitly now means mod degenerate. So the Serre spectral sequence is going to arise from a filtration on this chain complex, which calculates the homology of the total space. How are we doing on the time?
Got half and half.
Okay. So let's define FP of CC and P plus Q of X. I'm going to try to define the filtration for you. So I'm going to define FP on,
What is X?
it's going to be the filtration. So
X.
what's that? E. Thank you. So FP I'm going to look at, well, I'm going to define FP on cubes first, and then take the linear span, so that's a subset of cubes, and I'm going to take the linear span to define the filtration of the chain complex. So a cube will be in the subset FP inside all cubes if the projection, now I can give the projection a different name because P is suddenly indexing. If, so this is a cube mapping into E, I can project it down to B, I get a map here, that's sigma, sigma compose pi. If it factors, this is an N cube. If it factors through a P cube, sigma bar, where this map, IN to IP, sends T1 up to Tn to T1 up to Tp. So I use projection of the first coordinates. So a cube will be in filtration level P if it factors, if its projection to the base factors through a P cube by projection over the first P coordinates. So for example, what does it mean to be in filtration level 0? For a cube to be in filtration level 0, simply means what?
Maps into the fiber.
It has to map to a fiber. Because it has to project down through, maybe I should say filtration level 1. No, filtration level 0. It has to map down to the point 0, 0, 0, 0. So filtration level 0 of cubes and filtration level 1 is cubes lying over intervals, which don't have to be embedded, but over intervals in the base, and the interval is the projection onto the first factor. Now we have to think about the degenerate cubes now, I guess. No. So I'm working with non-degenerate cubes here. These image cubes might well be degenerate. But let's look at, suppose a cube in FP of the cubes on E projects to a degenerate cube. What does that mean? Well, that means this cube is sigma. And then if I compose sigma, having I n into B, factors through I P, but this is degenerate, which means it factors through IP minus 1, leaving out the last coordinate, the pth coordinate, which means it's really in filtration level P minus 1, which means sigma is in filtration level P minus 1. So that's maybe a cited summer point. Let me go over it again. So I'm thinking about cubes, well, I'm thinking about cubes that project down into the base. They cover a P cube in the base via the projection onto the first P. And I ask, when can that cube be degenerate? Well, I would say that cube mapping into the base actually factors through one more projection onto its first P minus 1 coordinates. And therefore the original factored into B. And therefore the original cube projects all the way down to a P minus 1 cube mapping into B, so it's in filtration level P minus 1.
Does any filtration P minus 1 thing come from this?
Yes.
But you only forget the last.
No, I'm forgetting the pth coordinate. That's sort of the magic of this. So I think you're asking, so we're talking about when is, so we defined a map, we're defining a map from FP of these cubes in the total space into, I want to map into the P cubes on the base. That's what I'm trying to define. So these are you divide out by degenerate cubes here. And the map is, take your cube here. Because it's in filtration level P, it factors through a map of IP into the base. Just take that map. You may have to divide out by it if it's degenerate, but that's all right. Just take that map. And I'm claiming the kernel of this is exactly F P minus 1. Because if a cube maps to 0 here, because it's in filtration level P, it factors through a P cube in the base. But that P cube is itself degenerate. But that means the original cube was in filtration level P minus 1. So we're defining a homomorphism like that. It's not an isomorphism. There's a lot more. I mean, think about the case when P is 0. These are cubes in a fiber mapping to the point. So we're going down here to the point, whatever fiber we're in, but there's lots and lots of cubes in that fiber. Now, fact, I want to do better than that. Yeah. So let's look at the non-degenerate cubes in V. So these are non-degenerate. So for each cube sigma, I have a fiber F sigma, which is simply sigma inverse the fiber over the first corner. So I have a cube down in the base, and here's 0, 0, here's 1, 0, here's 0, 1, and here's 1, 1. I look at the fiber over 0, 0. But of course, that depends on the cube downstairs. But I'm going to define a map from, well, so first of all, the cubes here, cubes in FP minus 1, produce non-degenerate cubes in B. So this group is a direct sum over the non-degenerate cubes in B of the things that map to that cube.
Don't you mean that F sigma is pi inverse of sigma of 0, 0, 0?
Yes. Thank you. Yes. So I take the corner and I take the fiber over. Thank you. So my cubes, my n cubes in E split up as a disjoint union over the sigma in non-degenerate P cubes, well, non-degenerate P cubes in the base of what I might call FP Q E sigma. So these are all the non-degenerate cubes in E that project to some P cube. These are the ones that project to a given P cube sigma. And so I can take the disjoint union over all the sigma, and I will get all the P cubes, all the N cubes that project to sigma, and that will give me all the N cubes in filtration level P minus the ones in filtration level P minus 1. Filtration level P minus filtration level P minus 1. Because these don't give me N simplices, they give me lower simplices. But the ones that are not in filtration level P minus 1 but are in filtration level P give me a P simplex, so I can partition this set out over the P, non-degenerate P simplices in P. And then taking linear spans, that writes Fp of Cc star E minus F E minus 1 of Cc star E as the direct sum over the sigma in QP of E Z tensor, well, it's a direct sum of the sigma in QP of B of this quotient. Those that map to sigma. Now I define a map from those that map to sigma that P plus Q now. non-degenerate cubes in the fiber associated with sigma. So the fiber over this initial point. And that's will be in degree Q. So I haven't used all my information yet. I've only been talking about what happens when you project to the base. So now I'm going to talk about what happens in one fiber at least. I'm not still getting all the information about the full cube, because all I'm learning about is how it projects to the base. So I know what fibers these things map into, the Q cubes. But I'm only going to record the Q cube over the first corner. Okay. That's what I did. So then taking the direct sum, we get a map of FP into the direct sum over sigma. Let's just put in a z, tends z to index by sigma, CCQ sigma, which is CC, well, so again, this is not an isomorphism, because I'm only recording in the fiber direction what happens in one fiber, and what's happening in the other fibers is varying away. I haven't control.
What does it say right after the direct sum? Z sub sigma?
Yeah, just a copy of the integers,
Okay.
but indexed by sigma. See what this is the chain complex on the base. These are the p chains on the base. It's a direct sum over the non-degenerate p simplices in the base of a z for each p simplex. So these are the p simplices in the base. The only thing I have to massage a little bit is this is not the q simplices in a given fiber over the base point. These are q simplices in varying fibers depending on our simplex. But now we invoke our hypothesis, our assumption that all the fibers have their homology canonically identified. Well, I guess before I do that, I have to take homology once. But you should recognize that this looks like CCP of the base, and this looks more or less like CCQ of the fibers, except unfortunately the fibers are varying, so I can't write it as a fixed tensor product at this point.
Wait, sorry, what was that map?
This map?
Yeah.
So this map was just take your cube sitting over sigma and look what sits over the first corner of the base. So that's a Q simplex in the fiber over that point. That's this map. And the trouble is the fiber depends on sigma, depends on the first corner of sigma. So that's why I had to have the fiber varying with sigma. Then I just add them all up and I get a map like this. And except, see, if this was all the same fiber, this would look like the tensor product of the chain complex of the base and the chain complex of the fiber, and then I could start taking homology and see what I got. Well, I can't quite do that. I have to take the homology first. And then I can identify the homologies of all the different fibers. So what I'm shooting for is that I'm not trying to identify E naught of the spectral sequence. Identify pieces of it, but it's bigger than these pieces. That is not an isomorphism for E naught. But I claim that E1 is the direct sum over sigma of Z indexed by sigma tensor the homology of F sigma. So, sorry. Is E1, E. Where these are the non-degenerate.
Now your fiber is independent.
Yeah, so now we can rewrite under our assumption about the action of the fundamental group, this as direct sum over sigma Q P D of this fixed fiber F naught. And that's nothing but CCP of the base into HQ of the fiber. So you get to identify the E1 term in the spectral sequence, not the E naught term. And it is the change on the base into the homology of the fiber. And the next claim is D1, mapping CCPB tensor H, the fiber into CCP minus 1 of the tensor H of the fiber is the boundary map for the change on B into the identity. And then you immediately conclude from these two claims, thus E2 is, I'm sorry, I'm doing, is HP of the base, which is so this is, without doing homology, so so these are the two basic claims. How much time do I have to do these? 10 minutes? 7 minutes. Okay.
Then you just write out the map.
Yeah, so let me try to write down the map. Well, sorry, from the same complex of the fiber back into FE. And the claim is going to be, so we have the restriction map that goes this way. That's the map we've already talked about. It's restricted the fiber over the corner. This is going to take something in the fiber over the corner and spread it out to give you a cube or a linear combination of cube, well, a cube actually, covering sigma. That's not going to be unique. There's a lot of choice in that. So, but it will be the case that if you start here, go in and come back, you get the identity. So, in other words, this map extending from what's over one fiber given to the base, what's over the fiber at the corner, extending into a full cube, when you restrict to the original fiber over the corner, you get back where you started. So it'll have that property, but it will not be the case that starting here, coming in and going out is an isomorphism. This is a much bigger group than this. There's lots and lots of cubes that sit over a given cube with a given fiber over the corner, obviously. But what you do is you construct a chain homotopy from.
John, where's this map H in what we've seen up to now?
Where is the map H? What?
Where does this come from? H?
Yeah, I'm going to tell you.
Okay. I
In
mean,
fact, let me just tell you.
where does it fit into what we've been looking at?
It's going to be a chain map.
Okay.
So I will have maps and homology both ways. So one composition, starting here, you get the identity of homology. I've got to try to argue by even another argument, uses something similar to H, that over here, this composition induces the identity on homology, even though it doesn't induce the identity on chains. But if I can do that, then these induce inverse isomorphisms on homology. So the homology of this, which is the E1 term, is the homology of the fiber. And then the extra, this is sum over sigma, so I get the sum over sigma of the homologies of these fibers as the E1 term, which is what I claim. So I need to prove the homology of this chain complex and the homology of this chain complex are the same. I have the restriction map, which is a chain map. Now I'm going to construct the chain map back in the other direction so that this composition is the identity and this one is chain homotopic to the identity. Okay, so let's just think about how I do H. Let's suppose P is 0 for a moment. No, suppose P is 1. So this is the P equals 1 case. So I have some chain in the fiber, probably a simplex in the fiber. So here's a sigma in the fiber. And I have my base, so that's not sigma, it's tau. And I have my base sigma. So at top and bottom, I just put sigma. And now I have the map defined on tau, that's what's given to me. So I'm trying to define H. So I want to say, what does H do to tau? Well, so here's tau. On its endpoints, I'll just put what I have to, which is sigma. And now I need to extend that over the whole square. Mapping into E, projecting down to sigma in B. Well, this is exactly the homotopy extension property. I mean, what we have here is a square modulo an interval on its boundary. So this thing is homotopy equivalent, homeomorphic, to the C that I've got here, these three parts of the boundary, across the interval. And I know what the homotopy is going to do down in B, because it just pushes across sigma. And I have it defined already on this part of the C, so I'll use homotopy lifting to extend it over the entire thing. Now, if tau were still doing P equals 1, but suppose tau were a two-dimensional cube. Okay. So this is sigma, and this is tau. I suppose by induction, I already have the extension defined over the boundary of tau. So that's the top, the front, the back, and the bottom. Those four sides. And of course the map is given to me over here. That's the map tau. So once again, I see tau crosses 0, union boundary tau cross I. That's where my map is defined, and it projects, wherever it's defined, projects onto sigma. Well, again, the 3 cube modulo, one face cross the boundary, one face union the boundary cross I is just like one face, and therefore you can do homotopy extension. So you go by induction. That's what you do when P is 1, and it's a similar argument inducting on both directions, which is higher. So that's how you define H. You use the homotopy extension property over and over again. And you define H so that it's compatible with the boundary map. That's what I was doing. I knew what H did on the boundary already, and I have tau given to me so that I can extend. Okay. Now, okay, so, but that's, of course, there's lots of choice in the homotopy extension. Now you have to think about what happens if you take a cube displayed over a non-degenerate cube in the base and with a given tau over the origin. You have two of them. You have to find a homotopy between them covering the trivial homotopy downstairs. It's exactly the same argument. There's another interval, but it's exactly the same inductive argument. And that proves that if you start here, restrict, so you start here with some unknown extension, you restrict, and then you use your homotopy extension to get a new extension. Those both cover the map to the base, they both agree on this one fiber, and you do exactly the same argument to produce a homotopy between them. So this composition is chain homotopic to the identity, so it induces the identity on cohomology, and that proves this claim. If you want more details, and you want to see the proof of the second claim, there in the notes. I think I've used up the time. Next, I want to talk about the cup product and cohomology. Now, that probably looks very familiar to all of you, but I want to examine it from the point of view of approximations to the diagonal and acyclic carriers, if you will. And that will lead us the week after to steam-line squares. So, okay? And we don't have any more vacations, right?
Hope not.